So the next thing that we want to do is we want to take our understanding of our average quantities, right, between 2 points in time, and talk about how we can turn those into instantaneous quantities at a single point in time. So let's just review very quickly, right? So when we talked about the quantities that we know between 2 points in time, right? Well, the position, and we said that's where you're located, X, Y, and Z. That's where you are at any point in time. And then the displacement is simply just the final minus the initial position. That's going to give us delta xi hat plus delta yj hat plus delta zk hat. And then if I take each of those components and divide by time, so that what I'm doing is taking the change in position and dividing by time, then that's going to give me the average velocity. And then graphically we said, well, if this is the vector showing your initial position, this is the vector showing your final position, then that vector subtraction, the displacement, is just a vector that runs from the tip of the initial to the tip of the final. The last quantity we talked about was average acceleration. And again, we said we're going to do the same type thing we did with the average velocity, just instead of wanting the change in position, now we want the change in velocity vector. So again, we're going to take our change in velocity vector, so final velocity minus initial velocity, and again divide it by the time between our 2 points in time. And so again, we have three equations here, one for what's going on in x, where we care about the x components of the velocity, one that's in y, where we care about what's going on with the y components of the velocity, one where what's going on in z. So these were the quantities that we talked about in terms of between 2 points in time. So how do we turn this into something instantaneous? Well, again, what we have here are for the displacement, the average velocity, and the acceleration, because these are really containing 2 points in time and really only information about those 2 points in time. What we said in class was that these are photos, right? I've got a snapshot of what's going on at the initial instant. I've got a snapshot of what's going on at the final instant. So how do I turn that into something about any instant? So in some sense, the question we're asking here is, how do I change the snapshot into a movie, right? So how do I go from just being able to see pictures at 2 points in time to being able to watch the movie as it runs at any point in time? So what we're going to do is we're going to say, well, we need to start, and our position now can't just be some value of the position. I need to really know the position as a function. So the situation here is, what I need to know is the position where all of my components are now functions of time. So this is sort of the key to being able to figure out what's going on at any point in time, is that I have to know, I'm going to start by needing to know the position at any point in time. So if I do that, if I know the position at any point in time, then I can calculate the instantaneous velocity by basically taking my definition of the average velocity and then simply taking its limit taking the limit of delta t as it approaches 0. Now I know that when I do that basically what I'm doing is I'm changing this expression into a derivative, and so this tells me that the instantaneous velocity is nothing more than the derivative of the position function with respect to time. Now again, this looks like just a single equation, but really, because this is a vector equation, it's really three of them. So this tells me that the x component of the velocity is going to be equal to, well, taking the derivative of the x position function with respect to time. The y component of the velocity will be taking the derivative of the y position function with respect to time. And the z component of the velocity will be taking the derivative of the z component with respect to time. So again, what I end up with is really three equations, and so here they are. Right? These are the three equations that are folded into this one vector equation. And again, this just tells me that for whichever component you're interested in, the easiest way to get that, or the way to get the instantaneous the component of the instantaneous velocity is to take the derivative of the position, that component of the position with respect to time. All right, so that gives me, I need a position function now as a function of time. So instead of just a what is the position, I need a position function. And then the instantaneous velocity, I'm going to take the derivative of each of those functions with respect to time to get the new components. And again, those will also be functions. So the x component of the velocity is still going to be a function. The y component of the velocity will still be a function. The z component of the velocity will still be a function. Taking its derivative hasn't changed that. So what I can then do is, again, if we think about starting with our definition for the average acceleration, and then we're going to take the limit as delta t approaches 0, so that what I end up with now is a derivative of the velocity with respect to time. So the acceleration, again, is nothing more than the derivative with respect to time of the velocity. And again, this is going to give me 3 equations. And so what I can do is sort of see each of these 3 equations in one of 2 forms. So I can either think of the x component of the acceleration as the derivative with respect to time of the x component of the velocity, or since I got the velocity component by taking its derivative, or taking the derivative with respect to time of the position, the x component of the acceleration is simply the second derivative with respect to time of the position function. So what we're doing is sort of setting up a structure here where we're going to start with a position function. We take its derivative once to get the velocity. We take its derivative a second time to get the acceleration. Same thing's true with both the y component and the z component. So again, my vector statement here, my vector equation, is really 3 equations, 1 for each component. So starting with my position functions, take its derivative once. That'll get you the component of the velocity. Take its derivative a second time, and that gets you the component of the acceleration. So this is what we're going to focus on, using sort of what we know about differential calculus to figure out what's going on in terms of the instantaneous motion once we know the position function for some particle.